thanks for coming to the starting day of the inauguration of our new center, aRtCS, the Arvind Raghunathan Center for Theoretical Computer Science. And as you know, we decided that there's no better way to start a center than to learn new things. So we're kicking off this event with a theory festival. And as you're aware from, the list of speakers that you can see, we have an outstanding program ahead. So I'll get out of the way of all the great talks that we're about to have. I'd like to call my colleague Raghu to introduce our first speaker.
Okay, our first speaker will be none other than Jaikumar Radhakrishnan. He's a faculty at IIT Bangalore. Previous to that, he has been faculty at TFR Mumbai for I think maybe 32 years. So he's well known for combining ideas from diverse subdisciplines of computer science along with combinatorics. In particular, he's well known for applying information theory and combinatorics in different areas of algorithms and complexity. So today he'll be speaking about today he'll be talking about lower bound for quantum circuits of limited quantum depth. Over to you, Jacob.
Good morning. My talk is about quantum computing, but it will turn out that most of the calculations that I will do will be somewhat classical calculations. In fact, one of the equations will actually be something that you have seen in probably your engineering class at some point. Okay. So before that, I'm very happy to be here at the inauguration of this center, and I cannot match Shweta's art, but this is the best my computer can make. So congratulations to everybody who's involved in setting this up. What I'm presenting today is joint work with Rohit Sharma Sharkar, who was postdoc at ICTS, and now he's moved to Barcelona. So for those of you who have seen quantum computing, you've heard about Grover search or database search. So I will review that, but we don't really need to know much about quantum at the moment. So the database search problem, one of the cases where quantum surprises us, is the following problem. So you've been given an array. So we've been given an array, and the task is to tell if there is even 1 in this array. So it's like you've been given some data and you want to know if there is even 1. Okay, so this is like computing the OR function. So now, for example, in this array there are no 1s, so your answer should be 0. And in this array, the 1 is in the second position. So the answer is 1 for this array. And you want to tell this array and this array, or arrays such as this, apart by making probes to the memory. Okay. So the question is, how many times do you need to look into the array before you can tell with high confidence whether there is a 1 or not? Okay. Now, so how do we think about this problem in theory? That you have a computer, it starts off in some state, let's say all zeros. It thinks for a while. It decides what to probe first, and then it makes a probe to this function. That means it submits to the function a location, 7. And then the function gets back and says, oh, in that position, I see a 0. And then based on this data and whatever other data you might have saved from the past, you think a little more. And then you make a query again, position number 21. And it says 0 or 1. And you continue. And at some point, you seem reasonably confident about the investigation you have done on this function, and then you decide to give the answer. Okay, good. So this is just trying to make a big deal of something that you write in 4 lines of code. Okay. So the question is, how many times do you need to probe F in any such circuit? Okay. So if deterministically, if you are not allowed any errors, then you can sort of persuade yourself that you cannot do anything except, look through all the entries, because the entry that you have not seen, suppose I keep telling you that it's 0, the entry that you have not seen could be where the 1 was. Okay. But on the other hand, if you're allowed randomness and a small probability of error, then if you, probe not all the locations, but randomly probe in some order a good fraction of the locations, then you can reduce your probability of error. So all this is very uninspiring. I mean, there's nothing. This is a rather nasty problem. You cannot do much even with randomness. But the surprise was that if these boxes now could do quantum things, they were quantum circuits, yeah, working with qubits. And then there is a notion of probing the memory in superposition, and you could probe the memory in superposition, and then based on the answer, do some more computation, etc., and then deliver the answer. Then it turns out, and this is the Grover's algorithm that everybody talks about, and you don't need to probe the memory n times. In square root n times, with high confidence, you can tell whether there is a 1 or not. Okay. So it's a big difference between n and square root n. And actually, almost simultaneously and completely independently, there's a lower bound was also proved. Okay. That is, you cannot do better than square root n. Yeah. So is this clear? So classically, we don't know how to do this thing. If we can build quantum computers as imagined today using gates and qubits, then it's possible to solve this problem using square root n probes. Okay. The trouble is, sorry, what am I doing? Yeah. What did I do? Yeah, good. We don't have quantum computers, and there are various models of restricted quantum computers that we can construct today. And one such is quantum circuits which are somewhat shallow. And what do I mean by that? So you see this number D. So you start the system in superposition. It's not very important what superposition is. You start the system in some superposition, and then a transformation is performed by the quantum computer. It's a unitary transformation. That's why U is written here. Again, not important. But it makes D probes to the memory. And somehow, your quantum computer is so fragile that after D probes, it sort of collapses. Okay? A measurement is performed on all of them. It just cannot hold its quantum state for very long. Okay? So this is one model, perhaps, of quantum computers that might come up, where you can hold the superposition for a short while. After that, you can extract whatever information you want, which is now a classical information. You can proceed again. Again, it will allow you, it can hold its breath for D probes, and then becomes classical. Yeah? Now, if you're given such circuits where presumably this D is small, can you still do quantum search? Yeah. So if D is not whole of square root n, yeah, the original Grover's algorithm says if the circuit can be quantum till the very end, then you can do it with square root n probes. But suppose I say that after every D probes, a measurement will be performed on your registers, and there is this block of D probes, a measurement is performed, and this state now becomes a classical random variable. Yeah, because a measurement has been performed. And then based on the contents of your memory, that is the registers, you can perform another computation, and you do it t times, and you need to give the answer in the end. Okay. So this is what I call a quantum circuit of small quantum depth, because the quantum state is held only for d steps. Okay. So the question is, if you're given such a circuit, how efficiently can you still solve that old problem of database search? Okay. And yeah, and the answer is n over d. Yeah. So if d is very small, for example, you say you can make 2 quantum probes, and after that I will forcibly measure your state. And then you can make 2 more quantum probes, and in that case, you basically don't gain much. It's still a linear bound. Okay. So what I want to do now is to show you how this n over d is achieved. And the main part of our discussion will be why n over d is necessary. Okay. And yeah, so, and I hope that there is something for everybody in the second part. Okay. So the first part, so you have this memory. The memory has length. It's an array with n elements. Okay. So you break the memory into buckets B1, B2, BD squared. Yeah. These are the first d squared locations. These are the next d squared locations, and these are the last d squared locations. Let's say d squared nicely divides n. Don't worry about that. Okay. Now, you perform a quantum search on this. That is, restrict yourself only to the first d squared entries of your array. And since the original quantum algorithm, now with n replaced by d squared, can run in time square root of d squared, that is d steps, this is a feasible computation for my model of small depth quantum computation. So you could do the computation on this, do the computation on this, do the computation on this, perhaps one after the other, at each time holding your quantum breadth only for d probes. Okay. And then what is the total amount of computation? Well, there are n over d squared blocks here. Yeah. Sorry, what did I do? This subscript should have been n over d squared. Yeah. Yeah. N over d squared. And each block needs this much quantum effort to search, and this gives you n over d. Nothing happened. Okay. Old-fashioned break the problem into sizes that you can, swallow. Okay. Sorry? You could do this in parallel. So the circuit, yeah, you could do this in parallel, but you will need that many copies of the circuit. Yeah, good. Yeah. So, lower bound. Yeah. Why can't you do better? Okay. So let me first review how the lower bound is usually proved in normal quantum computation without this restriction of limited depth. Okay. So the way it is argued is as follows. That is, there are n different choices for the database. That is, there are n special arrays. The first array or the 0th array has no ones at all. It's all zeros. And the jth one has 1 exactly in the jth place and zeros everywhere else. So these are n plus 1 different possibilities of the array. And our argument in the end will show is that you cannot be doing well on all of them. Yeah. If you don't make sufficiently many queries, then you can't be doing well on all of them. Of course, you might guess that the 1 is in the 7th place. And you might just go and probe the 7th location first. So for the array which has 1 in the 7th place, you got the answer immediately. But there are many other arrays for which you suffer. Okay. So the point is, that we will show that for one of these arrays, you will take your circuit will not have done very well. Okay. So, yeah. So suppose you had a circuit which had a certain number of probes into the memory, and let us say the state at the end is psi j. Yeah. So what is j doing here? So you take your circuit and suppose you put the jth array in the memory. That is, it has 1 in the jth place. In that case, the state will evolve and eventually settle down in the state psi j at the end. Okay. If you change your array to F5, then the final state that is produced is called psi 5. Okay. That's the terminology. Yeah. So a standard argument tells you that if you look at these states and look at how they are separated, so yeah, let me read this with you. So what is this? Psi 0 is the state that is reached when the array doesn't have anyone. That is psi 0. Now, instead of that, if you put the array which has 1 in the first place, that becomes the state psi 1. Otherwise, it is psi 2, psi 3, psi 4. Now, the question is, how much does psi 0 and psi 1, how much do they differ? That length is this. Okay, so quantum states are vectors, and you can take the usual Euclidean distance between vectors and you square them. Yeah, and it turns out that if your circuit only has d, makes the probes only d times, then the average distance between a state vector when the array should give the answer 1 and the state vector when the array should give the answer 0 is bounded by d squared over n. Yeah. But in the end, you must give different answers for these two states. Because in one case, the answer is 0. In the other case, the answer is 1. Now, that implies that this square distance for every j, every non-trivial j, 1 to n, must be at least 1/10. Okay? And here the average is bounded by 4d squared by n. In particular, for some j, this distance is less than 4d squared by n. Okay? And you compare 4d squared n and 1 over 10, because there is a d squared, that gives you d is at least square root n. Okay, let me say this again. So we argue that by averaging, there is some state which is very close to psi 0. You might be doing well for another state, but since there are n of them, your algorithm cannot be paying attention to all of them. One of them, it is not able to distinguish from the state that is produced when the array has only zeros. Okay, good. So this is how the standard argument works. This calculation exists, and I would just like you to remember this, that is the average distance between the final state when the array is all zeros and the array has exactly 1, 1 in one of the n positions, looks like d squared over n. Okay. All right. So this is how it used to be. Now we are in the situation where we are stringing together a bunch of shallow quantum circuits and hoping to answer the question. Okay. So how do we analyze this? Now the point is that you start the state off in the all zero state. Sorry, you start the system off in the all zero state, perform some computation and measure. Okay. So depending on what the state is in the beginning of the round, the state at the end is some random variable. Okay. So even though this is a quantum circuit inside, its behavior is like a stochastic matrix. You feed it something, what will be produced at the output will be a distribution on various states. Okay. And that state, one of them will be sampled and fed to the second round, and the stochastic matrix there will again spray the probability into various states. Okay. And one by one, these stochastic matrices operate on these random variables and produce the final state. Okay. The T at the bottom is because there are T blocks of D probes each, and the J at the top is because it is the jth array which has been fed to each of these algorithms. When J is 0, it means the array has no ones at all. Okay. So, yeah, so this is the definition, and we would like to show that, these different states, the state at the end for different values. So let me just say, this is the state at the end, the probabilistic state at the end produced when the array has 1 in the first position. This is when the array has 1 in the second position. This is when the array has n. And we would like to say that all these states cannot be far away from this. Okay? But here now we are talking about classical states. There is a little bit of quantum insight, and we will need to negotiate the quantum behavior of the circuit and the classical evolution across blocks. Okay. So how do we do that? So we try to bound the progress as the circuit progresses. Yeah. And yeah. So look at one particular block. This is the old picture. This is the old equation. And we would like to say that if two states are close, then after measurement, they cannot be made very far. Okay. Now, after measurement, they cannot be made very far. That means they remain close. But close according to what mathematics? Okay. And it turns out that there are many natural choices for trying to tell how close two states are in classical probability theory or statistics. Some of them don't work, and one of them works for us. And I would like to show you what doesn't work first, and then what eventually works. Okay. So is it clear what I'm trying to do? I'm trying to say that at the end of each block, no stochastic matrix has the ability to separate states much. These are classical states. The classical separation is not much. So if you string together these stochastic matrices, the final separation that is achieved will also not be much. But what should be the measure of progress? And let us look at one choice, L1. Okay, so this is the standard, many of you do cryptography, the total variational distance between distributions. Okay, so that is the L1 distance. So suppose we are able to prove that the average distance, L1 distance, between the final state when the array has 1 in the jth position and when the array has no ones at all is epsilon d. And why is this a d here? Because your blocks are allowed to make d probes. As d increases, presumably this number becomes smaller and smaller because you have looked at the array more carefully. Okay. And suppose we are able to prove such a theorem, then what sort of a lower bound will we get? Well, each time, each block makes a progress of only epsilon d. And if you put these blocks together, L1 has this nice property of being subadditive. That means the number of blocks you will need is 1 over epsilon d, roughly, because each block is making a progress of epsilon d. In the end, we need constant progress. So the number of blocks you will need is 1 over epsilon d. And each block makes d queries. So the total number of queries will be this. Yeah. No, so to get the desired bound, so if this number has to be n over d, let us do a back calculation. What sort of an epsilon d must we prove? Now, we will need to prove that epsilon d is bounded by d squared over n. Okay. Now, it turns out that this, unfortunately, is false. There are quantum circuits of depth d, which actually achieve an epsilon d, which looks like d over square root n. Okay, so we cannot just implement this idea because there is a counterexample to what we would need if this idea had to work. Okay. So L1 doesn't work. All right. So is this clear? I mean, feel free to ask anything. I mean, yeah. No, yeah. So, yeah, I mean, because I have a final proof which is correct. Yeah. Yeah. So it turns out that, yeah, it is true. Yes, one might ask, why is it that a quantum circuit is able, even with one query, yeah, even if you put D equals 1, yeah, the progress that it makes is 1 over square root n. It makes a progress of 1 over square root n, but it is a sort of progress that cannot be sustained by just classical means. That is, you cannot string together these quantum blocks, which have just one probe, and get the job done if you are forcing measurements after each probe. But any one probe makes good progress. Yeah. L1, yeah. Yeah, so it, I mean, yeah, so the question was, is in the inequality that I asked you to memorize, there was a square here, whereas here there is no square, etc. Yeah, so I mean, that is, yeah, so L1 usually we work with just the usual sum. But roughly that is where the square root advantage comes in quantum, because there is a square root involved when you go from probabilities to amplitudes. Yeah, but I don't have a clear answer at this point. Yeah. All right, so this doesn't work. But what might work? So, yeah, so statistics, a particularly pleasant measure is this KL divergence between two distributions, or relative entropy. Yeah, so this sort of justifies the title of my talk. So information-theoretic proof. Yeah, so you could say, all right, maybe what we should actually bound between the classical states at the end is not their L1 distance, but maybe the KL distance between them. Okay. Now, yeah, it's a good idea, especially because KL has this very nice thing called the chain rule for KL divergence. If you have many processes running one after the other, then you can write down the total progress as the sum of progresses made at each step. Even though silly logs, etc. are involved, it nicely breaks down into sum of progresses. It's an equality. Okay, the chain rule is an equality for KL divergence. And if somehow we are able to prove that the average distance between classical distributions achieved at the end is something like delta D, then if you do all this, you would see that, okay, delta D, can we bound delta D by D squared over N? Now, it turns out that after one probe, yeah, a quantum circuit can actually achieve unbounded KL divergence. Yeah, so roughly looks like a good idea, but there is a technical difficulty which I don't want to go into right now. So KL divergence can actually become unbounded, even though the L2 squared remains bounded. Okay, yeah. But one can, it turns out that this particular thing, that it is unbounded, can somehow be handled. You can slightly perturb the states by adding arbitrary noise artificially, and then you can make an argument and you can salvage some sort of a lower bound from KL divergence. Okay, so that's good. Yeah, and the lower bound almost looks like what we might want, but there is a log n over d here. Okay, yeah, and yeah. So for example, for d equals 1, that is, you make a quantum probe, I'll measure you. Make a quantum probe, I'll measure you. This only gives a lower bound of n over log n. Although in that case, we would think that you have not extracted the full advantage of quantum just by doing one probe, so you should need linear number of probes. This argument doesn't give that. Okay. So another bound, another notion of distance between distributions is this thing called Hellinger distance, which is not that popular in our community, but in statistics, this is a very important way of understanding the difference between distributions. And even if you do not care that much about quantum lower bounds, and if you have not seen Hellinger, I would like, this is something you can take away from this talk. Okay, so what is the Hellinger distance between two probability distributions? I will use the board. So if you have probability distributions are vectors. Yeah? So if you have n possibilities, these are n numbers, non-negative, which add up to 1. I mean, probability as seen as a vector is n numbers which add up to 1. That means they reside in an n-dimensional space. And where do they reside? They reside on this plane. Yes? Yeah. This is the point where the ith outcome has all the probability, other outcomes have 0 probability. This point perhaps is the point where all of them have uniform probability. This is the uniform distribution. So it lives here. Now, the usual L1 is when you have two different distributions here, how to tell them apart? Well, you sort of look at the two distributions and compute the area between them, between the two curves, maybe divide by 2, and that's called the L1 distance or the total variational distance. But there is another way of telling two probability vectors apart, and that is by taking their square root. So suppose there was this probability vector P1, P2, Pn. Yeah, let me just call it n. Then artificially sort of replace them by square root P1, square root P2. So now where do these vectors live? They don't no longer necessarily live on this, but they live on the sphere, because the sum of the squares add up to 1. So here is one probability distribution plotted on the circle. This is, let me just call it square root P. Yeah, this P, we have put a square root over it. Yeah, and then there is another distribution, which is square root Q. So now you have turned them into unit vectors, usual old-fashioned unit vectors, and just take the distance between them, this distance between them as vectors, n-dimensional vectors, and that quantity, if you see, is this. Yeah, and if you rearrange, you will see that it is this. But you should somehow, this should also be familiar. First of all, this should have been an A. Yeah, but this looks like the dot product of this vector yeah. So if two probability vectors have a high dot product, that means they are aligned in the same direction, then they have low Hellinger distance. Yeah. Okay. So this quantity has names in quantum information theory. It's called fidelity, and in old-fashioned information theory, this was called the Bhattacharya parameter. Okay. Yeah. So anyway, the Hellinger distance and the Bhattacharya parameter are closely related by an equality. Yeah. But there is a square here and things like that. But, yeah. So either you think in terms of whether the two state vectors have a very high overlap or they have a low distance. Yeah. These are interchangeable matters. When we do our calculations, sometimes it's useful to think in terms of dot products, and sometimes you think in terms of distance, and in particular when you use triangle inequality, this is more useful when you try to put things together, compose them. This is the quantity that is more useful. Okay, never mind. Now it turns out that suppose you have one block of D queries. Question? Yes, yes. You,
Square root, right? Like for continuous random variables, what do you do? Because the individual points, like you don't really have supported individual points, right?
and so the probability distribution, just take the square root.
Okay, of like the CDF?
Yeah.
Okay.
Not the CDF, the density function. Suppose you had density.
Okay.
Yeah, so I'm talking about continuous random variables which have density at each point. You take the density, multiply the two densities and integrate. Question?
So, another distance that you showed was not symmetric.
That doesn't bother me. Yes, so it was, the scale divergence, for example, is not symmetric. Yeah, I didn't even tell you what it is, but it's not symmetric, but that's okay. Yeah.
Okay, and I was a bit confused, but you see, when you make measurements,
Yes.
the nature would care about not a particular distance which you define.
Yes.
It would care about the Born's rule, for example, in quantum mechanics.
That's it.
That is probably intimately more connected to your first distance.
The L1 distance.
Yes.
That's right.
So that's my confusion, that I am doing a real experiment.
Yeah.
I don't care how you prove it. My point is that,
Yeah. So that is correct. So if you have made an observation, what appears, I mean, the way we think about it, is a random variable, or there are outcomes, and there is an event that you observe. Okay. And we want to know that that event, in one case, should have high probability, in another case, should have low probability. Then the distance between distributions that we really care about, if you want to tell apart distributions, is the L1 distance, because you're trying to say which event can tell them apart the most. Yeah. Now that is fine. And there is no argument against saying that in the end, what we care is the L1 distance. Yeah. But if we just stick with L1 distance and say, if I had such an L1 distance, what would the next block of quantum machinery do to the L1 distance? That is harder to control. Yeah. Meaning, what we know about the distributions after the first block is not just that the distance, L1 distance is small, some other distance is also small. And that imposes constraints on how well the second block can work on it. Okay. If we prematurely keep going to L1 distance, we are losing information about how close the distributions are in some other sense. And that's why it is true that in the end we care about L1, but at the intermediate stages, it's important to keep other parameters of a stronger induction hypothesis helps in mathematics. And you can say that these are stronger induction hypotheses that we are maintaining. Good. So, all right, what was I saying? Yeah. So at least we can say that if we look at the Hellinger distance after any block, this fact is still true. And this just turns out because when you had that inequality which I asked you to measure. Now, measurement does not hurt that inequality. The right-hand side still. So previously there used to be the usual Euclidean distance squared. Now you would replace it by Hellinger distance, but these are about classical objects. Yeah. The same inequality holds because measurement cannot create distance between two things which are already close. Okay. But this controls one block. What happens if I put these blocks together? Okay. In the case of L1 distance, I had a simple subadditivity property or triangle inequality which worked. In KL divergence, it was even more enjoyable. There was a chain rule which was actually an equality. Yeah. But in Hellinger, we know how to control the progress made in any one block. How do we combine them? It turns out that there is a wonderful chain rule. Yeah. And let me just say it in English, and then we will spend some time understanding the chain rule. So the progress of the circuit is less than the progress of the, actually this is an equality. So the circuit consisted of blocks. So we are interested in how much progress this composition of blocks makes. Okay. Now it turns out that the progress that the circuit makes can be written as the sum of the progresses made by each block. Right now, all fuzzy English. Okay. Yeah. And this progress will be measured in Hellinger distance, and I get to substitute 4d squared over n here. Okay. And now, since at the end, the progress has to be constant, if you rearrange this, you will get that the total number of queries, yeah, so the number t must be at least this, and since each block has d probes, the total number of probes becomes n over 16. So this is how the proof will end, okay? Provided somebody can prove for me this Hellinger distance, a chain rule for Hellinger distance. And, sorry, yeah. So, Jairam Tatachar, a former student of IIT Madras, now I think at IBM, in 2009 proved this wonderful inequality for Hellinger squared. Okay, and I don't know, some of you have seen this paper of Jairam's from 2009. It has this very provocative title called Hellinger Strikes Back. Okay. Yeah. So of course, so this was not the first paper that made our community aware of the power of the Hellinger distance. There were, for example, some of you are experts on communication complexity. So there was a paper of Jairam, Kumar, and others who used Hellinger distance to give a very nice information-theoretic lower bound for the disjointness problem. So anyway, for those of you who don't care too much about quantum, I would like to explain what Jairam's inequality says. Okay, so you have these t random variables, x1, x2, xt. Yeah, so you should think of them as x1 was somehow generated, then there was a process which generated x2 out of x1, then there was a process which generated x3, and finally xt. Okay. In our case, these processes happen to be d shallow circuits, but that is quantum. There is an inequality which has already been proved. We just black box everything into that inequality. We don't need to look into this box anymore. Okay, so good. So now, so you have these random variables, and I'm just introducing a notation. I'm sorry. So x1 to j is just the prefix. You just look at the first j random variables. x1, x2, x3, xt. Look at just the first j random. Then the next random variable is generated conditioned on the past. Yeah, because any sequence of random variables can be thought of as having first generated the first random variable, second condition on the first, third condition on the first two, and so on. So that is what I have here. So sorry, let's read this together. This is xi conditioned on the previous ones. Okay, so let me draw a picture. Okay, it doesn't matter. Yeah. Sorry. Yeah. No, these are whiteboard markers. Okay, good. Yeah. So, whenever you have a sequence of random variables, it makes sense to think of them as a tree. So, this is the random variable x. That means first you make a choice for x1, then x2, then xn. Yeah. So, depending on the value of x1, you generate x2 according to this distribution. Then a particular outcome arises, and then you generate x3, and so on. So this is the tree for X, there is a similar tree for Y. Now, you take a particular path in this and take the same path in this. And now here you measure this conditional distribution versus this conditional distribution. Okay. Now, this distribution and this distribution, these are honest to God distributions. We know how to compute their Hellinger distance. You compute them. And then averaged over all choices of points at this level, you compute the average Hellinger distance. So this particular quantity here is for a fixed I meaning level I, for a fixed level I, you make your choice X, which is the prefix, and then ask, after this, how does Xi behave versus how does Yi behave? And look at their Hellinger distance. Yeah. And then you take the average over all points, averaged according to which distribution? The distribution of X. Okay. This sum is an upper bound on the Hellinger square. Yeah. And sorry, I might have said take the Hellinger distance, I meant Hellinger distance square. Yeah. Sorry? That's right. Yeah. So the question was the conditioning of the Yi's is also with respect to X. That is true. You pick this point at random first. That means you take this random walk on this tree. Now you compare the two trees. Okay. The fact that this Y also had its own random walk is ignored. Okay. This is also true when you do the chain rule for KL divergence. The expectation is always with respect to X, and you take the distance. Yeah? Now, in our case, this X will be the states that are produced when the oracle has no ones at all. And these X's will be for various choices of the oracle. Okay. Now, if you put all this together, then, yeah, what did I do? Yeah, so if you use this chain rule, work with Hellinger square, you get this lower bound. Okay. Question? Sorry, I have 5 minutes. Yeah. Okay. Oh, so sorry. Okay. So yeah. So yeah, what goes into this proof? So I said I might tell you. Sorry. Question. Yeah.
Sorry, I had a question. So you take a path in the tree of X. Why would it exist in the tree of Y even?
Well, if it has, yeah. So if it has, so this path, this may not exist at all. Yeah. So let us assume that if it doesn't even exist, that is, there was zero probability for that. It doesn't matter. For this particular choice, you just put any distribution here. That's okay. Yeah. Okay. Yeah. For the moment, let's assume that all paths exist, but probably very small probability. You just do some continuity, just take the thing according to continuity. Okay. Yeah, but it's a valid question. So what goes? Questions?
So question. No, I was just curious that in your previous slide,
yeah,
was there any quantum or it's a general?
This is this one.
Yeah.
This is a fact about Hellinger distance. Okay. Yeah.
So,
question.
Yes. So the way you have drawn it seems that X and Y are independent of each other. Does it make a difference if Y is dependent on X?
It doesn't matter. I'm talking about distribution between two random variables. Right. Okay. So there is, sorry, I'm talking about the distance between the distributions of two random variables. So there is a marginal distribution of X, there is a marginal distribution of Y. If they live in the same probability space, these two marginal distributions are being combined, are being compared. That's all. I mean, the fact that there's no statement here about these random variables being dependent or not. X has a distribution, Y has a distribution. How much do they differ? Okay. Yeah, so just one second. I wanted to tell you that why did Jairam prove this? And so there, why meaning what paper why did he need this inequality? There is a paper, but why did Jairam prove this? Because he was taught mechanics. Okay, yeah. So remember in first physics course, or maybe nowadays even in high school, we are taught how to compute the moment of inertia of a body. Yeah. So the moment of inertia, usually you compute it about its center of mass. But suppose you computed its moment of inertia about its center of mass, and somebody cheated you and said, no, I want it about this axis. Yeah. Your old work is not wasted. You just assume that the mass of the body is located at the center of mass and make a little correction. You remember? I mean, yeah. This is so the center of mass about any point V, yeah, any point V where the center of mass, sorry, what did I do? Yeah, no, that's fine. Yeah, the center of mass is the sum of the squares. Sorry, the moment of inertia about any point V is the moment of inertia about the center of mass plus this correction. And if you now substitute for V one of the points Vj itself and take the expectation, you will see that if you were lazy in computing the center of mass not about, what all the nonsense. If you compute the moment of inertia not about the center of mass, but about one of the points, you'll get a wrong answer. But if you take the expectation over the points, it is exactly equal to 2 times the center of mass to be computed about this. This might have been an exercise in your mechanics class. Okay, just take the expectation of this with respect to the choice of J. Good, yeah. So this is one thing that goes into it. The second thing is a graph theoretic fact that if you take the complete graph on n vertices, it is a union of n minus 1 matchings when n is even. Okay, so yeah, if you take it's okay, don't worry, it's all right, I'm almost done. Yeah, no. So this is the complete graph. Yes. So n equals 4. There is this matching. There is this matching. These are 2 matchings, and then this one is also matching. Yeah. So any complete graph on n vertices can be written as a union of n matchings. And there is one more point called the cut and paste property of squared Hellinger distance. Yeah. So these 3 facts cleverly combined give rise to that inequality with the constant 4. Yeah. You don't get equality, but you can still bound it by these sums. And yeah, so that's all I wanted to say. I'll put up the reference. You should read Jairam's proof. And there's also a lecture note which nicely explains it. Yeah. So many of you think about hybrid arguments for doing very similar things in cryptography. This is an unusual kind of hybrid argument. Okay. And I'm hoping that my having described it to you today will make it find more uses. Yeah. So yeah, this is the reference. The summary. Yeah. So yeah, we understand what shallow circuits are, and we in the end proved a lower bound of n over d. This lower bound itself is not new. I mean, there was a more elaborate paper which proved many other things using very quantum sort of techniques called Zandri's method. But I think if you only are interested in this n over d lower bound, perhaps this is the way to go. Okay. Yeah, and what I wanted to advertise was Jairam's chain rule. Okay. So yeah, best wishes to the center again. Yeah, more formally. Yeah. Okay. Okay. Thank you. Sorry. Yeah. Question, Amit. Yeah.
What happens to other problems like element discreteness and you still have this model?
This model. So actually, the paper that I mentioned of Makran Sinha and others, they talk about this model for the collision problem. Okay, and there also they show optimal lower bounds. That is basically you do the natural thing, break the thing into this. I don't know if there is a general theory which says, that you can translate bounds where you have no restrictions to bounds where you have depth D by doing a little change in calculation. Okay. In particular, one of the techniques that is used for general lower bounds is the polynomial method. Okay. Somehow there is no polynomial method that I know of that is suited to the fact that after D queries you will be measured. Yeah. Questions?
So I was just curious that, quantum random walks
Yes.
are equivalent to search.
Yes.
So maybe quantum random walks with D coin tosses.
D quantum coin tosses and a measurement immediately.
And that also gives you a square root of n improvement. So let's say you have not n but D, you are limited by your coin runs out.
Yeah, coins run out after every D steps until your supplies come again. Yeah.
Probably.
This probably says what happens if after every D steps of a quantum walk, there is a measurement that is performed.
So in the
That constant is not 4, it is some other number which I have approximated by 4. I would suspect that the constant that Jairam has is optimal for his inequality. Whether that constant is important for my search problem, anyway, that 4 led to a 16 or something, that I have not investigated.
So in the interest of time, let's take further questions to the coffee break coming up soon. And let's thank our speaker again. I now call upon my colleague Raghu to present Jaikumar with a small token of our appreciation.